Amir Husain is founder and CEO of an award-winning machine learning, artificial intelligence-driven cognitive analytics company called Spark Cognition, which he launched in 2014 with support from Michael Dell's MSD Capital and other venture firms. Already in 2015, Spark Cognition is the first US company to receive the Nokia Open Innovation Challenge Award, selected from among hundreds of international innovators. He's a prolific inventor with 22 awarded and more than 40 pending US patents. He's author of the recent book, The Sentient Machine: The Coming Age of Artificial Intelligence. Ranked as one of the top 10 experts in the world in artificial intelligence, please give a warm welcome to Spark Cognition CEO, Amir Husain.
Thank you very much, Dave. Thank you. Wonderful. Well, hello, it's wonderful to be with you today. My talk is going to be focused on a couple of the topics that I talk about quite frequently, which is the impact that artificial intelligence is making in the world of business, and specifically this trend towards the dematerialization of value and its reappearance as software, and increasingly now AI software. But I'll also talk a little bit about how in the next wave of artificial intelligence adoption, because the work that I do and the work that my company does is very concerned with how you make AI real in the real world. How does AI deliver value to industrial systems and commercial systems? And we'll talk through examples of this. But to really get into an analysis of why is AI on the edge even important, and what does it do? And once we go through that, then we'll look at a few techniques that our own research group is working on, and of course in this wonderful community of many other experts from the silicon background and from the chips background. I'm sure it'll lead to hopefully an interesting discussion as to how we might adapt AI algorithms and go beyond some of the tried and tested approaches in bringing smarts to an increasingly low power, small form factor, and even slower systems. Okay. So with that, you may have heard this phrase before, software is eating the world. This came from Mark Andreessen. And the interpretation that I apply to this phrase is that software is dematerializing physical value from the world, and I'll give you an example of this. And that value is remanifesting as software. So this is a statement about economics. This is the statement about the advent of a new form of value that is displacing that which we knew. But my corollary to this statement is that now AI is eating software, and I'll tell you more about that as well. So if you consider a combustion engine here on the left, and you take a look at the number of parts that it takes to effectively build and run a combustion engine. You have valves, and you have timing belts, and you have spark plugs, and you have a distributor cap, and you have an EFI, and you have all of these components. On the right-hand side, you see an electric motor. And as automobiles move towards electric power plants, the question is, all the extra physical parts, the extra mechanical components, the larger amount of stuff you see on the left, where does that go? And the answer is, it dematerializes. It's removed. Its value is diminished and ultimately reduced to zero in the new economy. And what steps in to perform a lot of those functions, such as, for example, the function of an EFI, is a software routine. Software eats the world in a very real, literal, physical way. That's something to understand. And what's now happening is that the traditional paradigm of writing software, where a developer would sit at a workstation and in that mythical, perfect developer's mind, he knows, she knows exactly what to write. She's hacking away at the code, and every line is perfect, but it takes time. She needs to think through all of the scenarios that a physical system will encounter when her code is controlling that physical system. And that paradigm, what I call the if-then-else paradigm of programming, where all of the pre-thought scenarios are coming from a programmer's mind, may not be the best way to take intelligence and implant it into the physical world. So on the right-hand side, you have AI building gate patterns, teaching systems, made-up creatures that don't really exist, that have muscles and some sort of a structure of bones that holds them together, some sort of a skeletal structure. And here's the amazing thing. In this work done by Geitenbeek et al. In Europe, the genetic algorithms that were used to evolve these gates were not particularly trained or tuned to evolve gates in any specific kind of creature. You could have a creature like this and abuse it by throwing boxes at it. You could have a creature that looks like a kangaroo or a dinosaur or a giraffe or a man. You could even change the value of gravity, the gravitational constant, on the surface that these systems were working on. And yet the same genetic algorithm was finding ways automatically without anyone writing any piece of code. Here a creature is walking on an undulating surface. They learn all these things. So imagine the equivalent. What would the equivalent have been had programmers sat down and specifically encoded the gate patterns for dozens and dozens and dozens of these creatures in various different environments? This is what I mean when I say AI is eating software. The actual work that we used to do as programmers, a lot of that work, not all of that work, a lot of that work can now be done with algorithms. Now, with this being said, what I wanted to set the stage on was the fact that artificial intelligence certainly is a technology. And it's been in the works for many years. And there's a lot of questions raised when I talk about AI, and even in response to the book that I wrote. Questions are, well, we've heard it before. We heard it in the late 50s. We heard it in the 70s and 80s. We heard it in the 90s. What's different this time? And what's different this time is that artificial intelligence has progressed to the point where it is undeniably delivering business value. That's what's different. You can make a lot of innovations and you can make a lot of progress in the lab. Shaky the robot was a marvel technologically, given the capabilities of the time, but you couldn't really take those capabilities and transform them into something commercially viable. We now do this every day. AI is making money. That's what's different. And underneath all of this is the fact that that money is being used to fuel an ever greater reinvestment in the kinds of platforms, capabilities, data acquisition, talent, and so on and so forth. So those things are fundamentally different. You'll hear people say, oh, well, now we have more data and we have more compute and we got the cloud and we have sensors. Of course, I say that too. Those are reasons. But I think the meta reason is that AI now makes serious money. So where will AI impact the world? I know of personal experience, based off of personal experience, that artificial intelligence is already significantly impacting the area of energy, where systems are being made more stable, where remaining useful life is being calculated by our systems and many others. In aviation, where natural language processing is being applied to provide prescriptive solutions before an aircraft lands. The technician already knows exactly what to do with the plane. Doesn't have to leaf through 27 manuals. They see the prescriptive solution right there. In defense, I sit on the Center for a New American Security, which is a DC think tank, their AI committee, and that committee is focused on national security. I understand all of the work that's going on the defense side, and let me just tell you that it's very significant. Some in the defense community wanted to go faster. Internationally, as you know, this has been a great topic. Several other near-peer states have talked about their AI policies materializing in the 2030 timeframe. The US similarly is thinking about this. So defense will be an area. Cyber, we all know about this. There's hardly a way to keep up with the new cyber threat without using AI systems that can adapt to the zero-day environment that we now live in. And healthcare, where so many things go undiagnosed and we suffer the tyranny of the bucket illness, an illness which is not really an illness, it's just a random collection of symptoms across many illnesses that look the same, but we don't know how to separate these, and so we treat the symptoms and not the underlying cause. Diagnosis has a long way to go in the field of medicine, and this is another area where artificial intelligence can help in tremendous ways. And today, like I said, AI is making money. But how is AI deployed today? Well, AI is deployed basically in the sense that you've got, at the bottom there of that graphic, you've got the kinds of applications that we use today, whether it's a smart speaker or whether it's an antivirus program or whether it's an industrial asset. And each one of these elements out in the world, federated and distributed out in the world, whenever they encounter data, they basically ship the data back across the cloud, across a network, to a system, a data center, that then has custom AI accelerators. You know, if it's a Google data center, they might have TPUs. If it's a Microsoft Azure data center, they might have the accelerators that Doug Berger's team has put together. But the idea is that every time you encounter something meaningful, stop thinking, package the data, ship it across the wire, and Big Brother, back in the cloud, will tell you what to do. And the way that this gets delivered to developers today is in the form of APIs, right? So, for example, some of the APIs that are very common, I have a small piece of text. I want to figure out what the sentiment on this is. This is a very common service that a lot of AI programs use. Well, make a call to the cloud to figure out what the sentiment is. I've got to figure out if this time series data has an anomaly. Well, ship the data to the cloud, and then the cloud will tell you whether it's an anomaly or not. Now, you might say that, well, whose cloud? Is it some vendor's cloud, or is it my own corporate cloud? And of course, all those things matter, but this does raise data governance concerns, this model, for a lot of people. A lot of companies are now very, very concerned about where their data goes and who learns what from their data. So, in my view, this argues for, yes, the cloud existing the way it exists, but also options for hybrid clouds, where companies can take these kinds of capabilities and bring them in-house. But even more importantly, if you think about the basic paradigm, we, which contain intelligence in our head, right, in some limited form of intelligence, 20 watts of power in our brain, as we walk across the street and we encounter something anomalous, some new kind of obstruction, and that exact obstruction we've never seen before, what do we think? Oh, let me go back and look at go to the library and see what this thing is and then figure out the best way to get around it. No, we don't go back to Big Brother. We don't go back to an information repository. We have the local intelligence to be able to say that, look, this might not be exactly the kind of issue that I've seen before, but I have a way of getting around it. I can compute a path that goes around it, and my generalized knowledge gathering of the past now allows me to locally make the decision and get around an issue like this. Of course, this is a trivialized example because I wanted to illustrate that this idea that anytime you need intelligence, you've got to go back into the cloud, this is not natural, for sure. So intelligence at the edge is critical. That's the point that I'm getting to. But you might ask, why? Why is it critical? Why can't we just keep using the cloud? What's wrong with it? So earlier I talked about data governance and some concerns like that, but there are a lot of reasons why. All of these reasons, I am not giving you, nothing I am saying here is hypothetical. We've worked in each one of these areas. We've built applications in each one of these areas, and we've deployed them with customers in each one of these areas. So what I am telling you is not just my opinion. What I'm telling you is real data sourced from customers and real customer feedback. So for example, in industry, we have a large number of industrial clients. We look at being able to predict remaining useful life, when a system will fail, when a $50 million to $100 million turbine will fail, when a wind farm will see a malfunction, when a large industrial pump used in large oil and gas facilities will see a malfunction. And we do this with our automated model building technology, where AI builds AI, and you don't need as much domain expertise, and then you can predict these outcomes. In this case, the amount of data being measured and generated at these high-speed analog assets is so great that the current paradigm is to average down the data. You measure the data, then you average down the data, then you store it in some sort of a DAC cache, then you move it to a data historian, and then you worry about shipping it across the network. Now, in that downsampling, what do you lose? And if we had intelligence at the edge that was able to learn from the high-fidelity, raw, high-speed data, what could we find out? So this is one case where it just doesn't seem reasonable that a substantial reduction of information will lead to better performance. By putting intelligence at the edge, we can make that more performant. In aerospace, I think that we are about to enter a world in which the largest commercial market of our living memory is about to be created. And that is aerial autonomy, autonomous aerial autonomy, basically urban, disruptive aerial autonomy. And you see signs of this. This has been going on for many years, but I think there will be a large number of vehicles across a large number of geographies, and many countries have started to sort of adapt their laws and regulations to enable some of this. The UAE in particular, where I was recently, they have appointed a minister for artificial intelligence, and their RTA, their Road and Transport Authority, has a program now with a defined goal of putting a flying taxi that provides service to the city within the next 2 to 3 years. So these things are coming. Now, in this new world, is our current system of traffic management appropriate? Is our ability to control these aircraft autonomously when we rely on the cloud, is that even acceptable? No. You have to have intelligence at the edge in this application. You extend this a little bit further and you start looking at defense. I don't know of many commanders in the US Navy that would say, sure, I'm comfortable running my prognostic system with the cloud. I'll just figure it out when I'm under electronic warfare attack. And this happens a lot now. In the conflicts that have occurred in Europe, in what has been deployed already in the Ukraine, in what Russia demonstrated during the recent exercises that they did just a few months ago, these are now real concerns. Notice, this is not about good and bad. This is just about what is. This is happening. So, to the extent that the people that are concerned about these issues are wanting to figure out ways to make AI viable for them, ignoring real AI at the edge means that those use cases will not be fulfilled with AI. For cybersecurity, signature-based security is dead. It's completely dead. And today you have automated mutation tools, you have tens of thousands of new types of attacks being launched, each of which have a different signature. And that whole idea of being able to take a signature database and simply filtering malevolent files out based on a signature match, that's so passé. That doesn't work anymore. So you need artificial intelligence to be able to identify behaviors, to do a static analysis of a file, and to be able to do this even when that AI system is in a disconnected environment. You can't just keep dialing back to the cloud. So putting AI at the edge is critical for cybersecurity. Let me show you an example of an AI system that we built. And also, this is one of those that has to be an edge system. So what you see is an aircraft simulator for a large passenger aircraft. And then on the left, you have autopilot, the traditional autopilot, and on the right, you have autonomous pilot. Autonomous pilot is being controlled by our AI. What we simulate here is a number of failures. So as the aircraft is building speed on the runway, the left engine of both aircraft has failed. Now notice the stick on both sides. The left engine on just autopilot has already gone almost off the runway. The aircraft on the right has taken off and is aggressively maneuvering the stick to save the aircraft. And you can see how the horizon line is just jumping around in the left case, which is non-AI. And let's just say that we pause this before the bitter end, which we don't wish to show. So the net here is that what is this application? This is an application that can revolutionize aviation. Because what we're doing here is we're shaving off a significant amount of time in that decision that a pilot makes to abort or continue with a takeoff. When something wrong happens and you're hurtling down the runway at 120 knots, you have fractions of a second as a pilot, as a human pilot, to make the decision as to whether you want to continue to take off and then come back, or whether you're going to try and brake because you know that a takeoff is entirely unviable. And this is a life and death decision. An AI system that has improved both the quality metric, the quality of the decision, and has cut down the time is tremendous. But it cannot be a cloud-based system. The latencies don't support it. The use case doesn't support it. But it is an absolutely critical system that makes me very, very proud we're associated with this work, because our mission is to drive artificial intelligence technologies for the most important interests of humanity. And this is the saving of life. This requires edge AI. OK, so next chapter, if you will, in the talk. Again, I started off telling you why I think artificial intelligence is so seminal. It's not just about the technology, it's about the rewriting of economics and the rewriting of how we see value encapsulated in physical objects. It's a change of how we view the world and what we ascribe wealth to. The second part of the talk goes into the kinds of applications that simply cannot be done with AI in the cloud, for which edge AI is absolutely critical, which I think is very interesting for the semiconductor industry. And now the third part of this talk is, well, OK, how do we put AI at the edge? Now here, what I'll say is that, I'm sure you can come up with many other approaches. But look, one of the things that's being done is that we're looking at companies that are investing in ASICs, right? Even though I didn't put the names of the companies on the hardware in the top left quadrant, for those of you who have seen this hardware, you know where it came from. These are boards created by large companies that are deep learning accelerators of various types that work with their ecosystem. And at the same time, they're also miniature PC-compatible, like USB sticks, basically little GPUs on a USB stick that then work with a framework that allows you to do neural networks. So there's that kind of thing going on. Then below that, there are existing ML techniques, existing machine learning techniques with no framework modifications or anything necessary, just on ever smaller, small form factor conventional compute platforms. That board is a Core i7 board. It has expansion. It can take a lot of RAM. It's pretty small. Power consumption has gone down over the last few years. There are some applications where that'll do. But then there's the really, really small. And the reason why the really, really small to me is fascinating is because if we're going to truly federate and free artificial intelligence and this promise of universal, ever-present, omnipresent decision-making and smart objects all around, truly making the universe programmable, that's going to happen when you can build neural networks that are miniature, that run on truly miniaturized devices with minimal power constraints. So how can we do that? Right? So one approach that we've been looking at on the top right is to say that, look, artificial intelligence isn't just deep networking. And this is one of the things that happens in the community when one particular way of solving a problem becomes fashionable, then everybody chases that way of solving the problem. And in that, sometimes we lose sight of the fact that there are, if you look at AI textbooks, there are many other chapters other than the chapter on connectionism. And to solve many problems, there can be approaches that are less computationally extensive that can be implemented on some of these smaller chips. So that's a very conventional, practical way of saying, we already have this, why wouldn't we think this other way? But the last one is technically very exciting and intriguing to me. And this is research work that we've been doing at Spark Cognition under our research team, which is run by our Chief Science Officer, Professor Bruce Porter, who's also been two-time chairman of UT Computer Science and is a 35-year AI veteran, one of the top people in natural language processing in the world. And Professor Porter has a team of researchers who have been investing a lot of time and energy in this area called lightweight neural networks. And I'll tell you a little bit about what lightweight neural networks look like. So the idea here is on the right, you actually see a video, which is actually a console capture from a $2 ESP8266 controller that is running a neural network written by us, which is capable of both learning, so backprop, as well as feed forward, giving responses. So now you can look at a small little $2 controller with Wi-Fi and a small neural network that can both learn as well as provide feed-forward responses. And this device itself is wired up for all kind of analog inputs and so on and so forth. This is a perfect brain to put into just anything. It's a perfect brain to put into anything and have it start learning based on its interactions. Right? So this is the kind of thing that's interesting to us, because you can now start to put this a couple of bucks, and you can start to put this really anywhere you want, on an industrial control, in a child's toy, in literally next to a valve. You can monitor anything you want. So this is exciting, and we've seen some good results. But here is where we've seen absolutely mind-blowing results. I did not believe these results when I was first shown these by my team. So I was talking earlier about cybersecurity, and Deep Armor is our cybersecurity product that uses artificial intelligence to identify threats and to immediately find zero-day attacks that have never been seen before. And in order to use this, we have trained Deep Armor on a massive number of both malware as well as good files, good reference files. And we built a massive, deep, complex network for Deep Armor to be able to detect these issues and to then classify these issues. When our research team, which was not working directly with the Deep Armor product team, when the research team started to look at lightweight networks, they went internally in the company and they said, could somebody that's building a product give us a problem to solve with this technology? We're hopeful we'll be able to drive great results. So they applied their lightweight neural network technology, which has one commonality with many of the accelerated AI boards, the deep learning boards that are being built now, in that it doesn't use floating point math. But the other thing it does is it has very specific sparse topologies, very specific sparse topologies. And it's able to actually drop a large number of features, simplify the computation, eliminate structurally, eliminate floating point, and if you look at that last finding, okay, a 6-neuron network approaches the accuracy of this big, deep network that we had created for Deep Armor. So what does this mean, and why was my mind blown? Because we can take this technology now and embed it on every controller. Every controller has the ability to defend itself. From a cyber perspective, the whole approach in how you defend these systems can be changed. So that is, it's a significant and a disconnected environment without requiring updates, because it's machine learning based. It doesn't need the latest download of signatures. This is a fantastic piece of evidence that shows that there is a lot of potential when it comes to innovating on the software side and when it comes to really thinking through what we're trying to solve and optimizing our algorithms to exactly the kind of problem and exactly the kind of hardware capability we have. Okay. So with that, I will end. We certainly have another 5 or so minutes. There's much more information on my work, on Spark Cognition's work, all our products, everything I've talked about, as well as the book. But we have 5 minutes. If there's any interest in questions, I'd be happy to take them. Please.
I'm impressed by that last example you just gave of being able to take a very simple network and embed it everywhere. But can it really stay disconnected? I mean, as threats keep changing, how much power do you really get in that very simple network? Or do you Wi-Fi enable it so that it continues to be powerful?
Yes. So, I don't think the metric is that it needs to be disconnected forever. But realistically, when you think about antivirus solutions today, they're literally updated every day. A system like this can probably go a quarter or two without being updated. And then in a regular upgrade cycle, can have an alternate model deployed to it. And that model, of course, is just a definition file. So instead of all the data for retraining, what you're really sharing with this network is a few vectors that define the new weights and connections in the network that it's using. So it's really, really tiny. And it's actually information compression of a pretty extreme degree.
And I'm sorry, just one quick follow-up. But, one of the issues with networks like this is you never know why they came to the decision.
Very, very good point. Explainability. So explainable AI is a core area of work. And for each one of our products, the actual manifestation of how to explain to a human has to change. But for these small networks, explainability is actually much easier. Because in a large network with thousands of nodes and tens of thousands, hundreds of thousands of connections, there's just no hope that you can work it out. But here you can look at this as a graph. And the actual function that can be extracted from a 6-node network will be a relatively simple function. So even with function extraction approaches, a smaller network is by definition more explainable. If you look at the original work on perceptrons, and you look at the argument around why it couldn't address certain types of operations, those perceptrons sort of intuitively, given their small size, intuitively indicated why that problem occurred. So smallness is a good thing, and it helps explainability. Okay. Well, thank you very much.
Thank you, Amir. Really appreciate it. Thank you so much, Amir. That was really fascinating. Thanks to you, I think my mental hard drive is, again, overloaded. Just so you're aware, Amir will be signing his book afterward in the theater's lobby at 11:30 or right after the panel. You're encouraged to take advantage of the opportunity and delve deeper into his thinking on AI.